Srimati R. Padmavati, Head of Department EC, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics. So, this module includes the operational amplifiers in which the comparators, regenerative comparator and square wave generator. So, this is the comparator circuit. We have already discussed this comparator circuit in open loop configuration of operational amplifier. So, what is a comparator? This is going to compare the input signals given to the two different input terminals of the operational amplifier. Based on the magnitude of the input signal, the output gets transition between the saturation voltages, that is minus or plus V saturation. This V saturation is slightly less than the supply voltage given to the positive terminal and the negative terminal. So, here this is the input V1 is given to the second terminal and reference voltage is given to the third terminal. Here the input voltage is always compared with the reference voltage here. If the input voltage is lesser than, so here the input voltage is given to the second terminal and to the third terminal reference voltage is given. Always the input voltage is compared with the reference voltage, and this input voltage, if it is lesser than the reference voltage, then the output is positive because the input voltage is given to the negative terminal and reference is given to the positive terminal. So, whenever the voltage at the positive terminal is higher, then the output is positive. Whenever the voltage at the negative terminal is higher, the voltage is negative. So, here this is the input signal and this signal is compared with the reference signal, which is a DC signal. Input signal is an AC signal. Here, according to this circuit, the input signal at this point, up to this point, the input signal is lesser than the reference voltage and the reference voltage is higher, which is given to the positive terminal. And so, if the reference voltage is higher, then the output of the circuit is positive. So, up to this point the output is positive, and after this point up to here the input voltage is higher than the reference voltage. So, here the input voltage is given to the negative terminal, and if it is higher, then the output will be negative V saturation, and so it gets transition to a negative V saturation until the next intersection. So, here again if the input voltage is lower than the reference voltage until lower than the reference voltage, the output is positive V saturation. Similarly, it goes on. So, here this reference voltage may be a positive reference voltage or a negative reference voltage, and you can give the input signal either to the negative terminal or to the positive terminal. So, in either way, if Vi is greater than V reference, then the output is minus V saturation. If Vi is lesser than V reference, then the output is positive V saturation. So, this is for inverting comparator. Why it is inverting comparator? Because the signal is given to the negative terminal. So, it is an inverting comparator. For a non-inverting comparator, it is just reversed. If Vi is greater than V reference, so Vi is given to the positive terminal, so the output is plus V saturation, and if V reference is greater than Vi, then the output is minus V saturation. This is for non-inverting comparator. This is a simple concept, and also you can say this comparator is acting as a switch because it is switching between two voltages called the positive saturation voltage and the negative saturation voltage. See here, this voltage is positive saturation. These are the positive saturation values and these are the negative saturation voltages. So, either it may be a positive saturation value or it may be a negative saturation value. So, the output always switches between positive and negative. So, it is otherwise called as a switch. The comparator is otherwise called as a switch. So, what happens if the reference voltage is 0? What happens if the reference voltage is 0? So, here this V reference is at the mid of this sine wave. So, the peaks of the sine wave is symmetric about this reference voltage when the reference voltage is 0. So, you can say that whenever the input voltage is crossing 0, the output will get transition, right. So, if the reference voltage is 0, this comparator is now said to be a 0 crossing detector. Instead of V reference, this is 0 volt and here you are giving input signal and there is no feedback since it is a comparator in op-amp in open loop configuration. So, this is said to be 0 crossing detector. Whenever the input voltage crosses 0, this input voltage crosses 0, then the output will get transition. Whenever the input voltage is positive, that is greater, the output is minus V saturation, and whenever it is lesser, then the output is plus V saturation. So, this is one of the important application of a comparator, 0 crossing detector. It is one of the most important application of a comparator. And next is regenerative comparator. What do you mean by regenerative comparator? If positive feedback is given to the comparator, gain can be increased greatly. The transfer curve of comparator becomes more close to the ideal curve. So, transfer curve, did you remember the transfer curve like this? Ideal is transition like this, and this is practical. This becomes more close to the ideal curve. That is what this means. If the loop gain A beta is adjusted to unity, then the gain with feedback becomes infinite. So, what is the formula of the circuit if it has a positive feedback? It is the open loop gain divided by 1 minus the product of the closed loop gain and the open loop gain. So, I can write it as A by 1 minus A beta. So, this is the equation for the circuit if it has a positive feedback. So, where A is the open loop gain and beta is the closed loop gain. So, this A beta, if it is adjusted to unity, then the gain with the feedback becomes infinite, right. The gain with feedback becomes infinite. This is equal to the gain with feedback. This equation is for the gain with feedback. So, if it is adjusted to unity, if A beta is adjusted to unity, you will be getting 0 here. So, anything by 0 it is infinite. So, the gain with feedback is infinite. This results in an abrupt transitions between the extreme values of the output voltage. So, if it is very high, the gain with the feedback is very high, then this practical transfer characteristics will be very close to the ideal transfer characteristics. So, it will get abrupt transition, right. It will not take any rise time to reach the final value. That is what it means. In practice, it is not possible to maintain A beta equal to unity, and we are designing it, it must be greater than or equal to unity. So, a value greater than unity is chosen. This gives an output waveform virtually discontinuous at the comparison voltage. Now, the circuit exhibits a phenomenon called hysteresis or backlash. We will see what it is. So, this is the circuit of a regenerative comparator, and the other name of the regenerative comparator is Schmitt trigger. Schmitt trigger is the other name of the regenerative comparator. So, why it is called as regenerative comparator is, if you give positive feedback, the gain is regenerated, the output is regenerated. If it is a negative feedback, it is degenerated. Here, some part of the output is given through the resistors to the positive terminal, and this is a positive feedback circuit, and so the output is getting regenerated, and so it is a regenerative comparator, and the input signal is given to the negative terminal of the operational amplifier. So, what is the beta here? It is through these resistors you have to find out what is beta, and this is the input output waveforms, how it is going to get transition between the plus and minus V saturation. So, always for the comparator, what is the output? The output will be either switches from positive or negative V saturation, that is the output of the comparator. Here also the output of the regenerative comparator is either positive or negative V saturation based on the input voltages compared with the two reference voltages here, VUTP and VLT. Here it is VUT is upper threshold voltage and VLT is lower threshold voltage. So, in the comparator we have seen input voltage is compared with the reference voltage. Here what happens if two reference voltages are given? Here VUP is the upper threshold voltage and VLP is the lower threshold voltage. With these threshold voltages, the input voltage is getting compared. If the input voltage is compared with the upper threshold voltage at one time, for the next time it should be compared with the lower threshold voltage, even though it has upper threshold voltage before the lower threshold voltage, right. And if this time is with the lower threshold voltage, and for the next time it has to compare with the upper threshold voltage, right. So, it will compare, the input voltage is compared with upper threshold voltage, and next is lower threshold voltage, and next is upper threshold voltage alternatively, right. If whenever the input voltage crosses the upper threshold voltage and lower threshold voltage alternatively, the output gets transition based on the voltages or the amplitude of the input and the V reference voltage. So, here consider the output of this Schmitt trigger is positive V saturation. Consider the output of the Schmitt trigger or regenerator comparator is a positive V reference, then the voltage at this positive terminal, is say plus beta V saturation, or you can say that is the upper threshold voltage. When the output of the regenerative comparator is plus V saturation, then the voltage at the positive terminal is upper threshold voltage through these feedback resistor and the resistor here, and we are having a positive voltage here, right. And now the voltage is compared, the input voltage is compared with the upper threshold voltage, and if it is less than the upper threshold voltage, then the output is positive. Always the comparator concept. If the input voltage is higher than the upper threshold voltage, then the output is negative. Now, if for the case 1, if the output voltage is plus V saturation, now the voltage given to the positive terminal is upper threshold voltage, and now the input voltage is compared with the upper threshold voltage. If it is high at that time, then the output voltage is minus V saturation, because the voltage at the negative terminal is higher than the upper threshold voltage. So, the output gets transited to minus V saturation. Now, what is the voltage at the positive terminal? Here it is lower threshold voltage. So, when the output is positive V saturation, the voltage at the positive terminal is upper threshold voltage. When the output is negative V saturation, the voltage at the negative terminal is lower threshold voltage. Now, if the input voltage is compared with the lower threshold voltage. So, if the input voltage is less than the lower threshold voltage, then output becomes plus V saturation. So, it gets transited from minus V saturation to plus V saturation. We can have a break. Come back after the break. So, we have seen the Schmitt trigger operation now, and this is the input output waveforms. So, here we VUPT and VLPT both are the voltages at the positive terminal of the op amp alternatively, right. So, this input voltage up to this point is lower than V upper threshold voltage. So, input voltage is given to the negative terminal, and so the output is positive V saturation because the threshold voltage is higher up to this point. So, positive V saturation up to this point, and after that this input voltage is compared with the lower threshold voltage. So, at this up to this point the input voltage is higher, and input voltage is given to the negative terminal, and so the output is minus V saturation. Whenever the input voltage given to the negative terminal is higher than the positive terminal, we know that the output must be negative and the output must be saturated value. So, it is minus V saturation up to this point, and after that this time it was compared with the lower threshold voltage, and next time it has to compare with the upper threshold voltage because we know that the output gets transition from positive V saturation to negative V saturation. When it is positive V saturation, the voltage at the terminal, positive terminal is upper threshold voltage. When it is negative V saturation, the voltage at the positive terminal is lower threshold voltage. So, alternatively the voltage at the positive terminal becomes plus upper threshold voltage or lower threshold voltage. So, now this voltage, input voltage is lesser than the upper threshold voltage. So, what does it mean? The upper threshold voltage is higher, it is given to the positive terminal, and so the output must be positive V saturation and so on. In this way the output is getting transited. The input voltage, whenever the input voltage exceeds the threshold voltages, then the output gets transition. This is what the function of the schemic trigger. The voltage levels are called upper threshold voltage and the lower threshold voltage, and we said that there is a backlash or a hysteresis if the gain is tremendously increased. That hysteresis voltage is calculated from the threshold voltages. So, now VUT, the upper threshold voltage, is calculated as, we know that in the circuit there are two resistances, say this is R1, this is R2 and this is V sat, here Vi. So, if this is positive V saturation, here VUT. VUT is calculated from these potential dividers, and it is, here we are giving reference voltage, it is not grounded. Here at the end of R2 we are giving reference voltage. So, here there are two voltages to calculate this VUT. So, what you have to do? You have to apply superposition theorem. Superposition theorem is, whenever two or more voltage sources, you have to calculate the output keeping one voltage is active and all other voltages are inactive, and similarly for all other voltages. So, here there are two voltages. So, I am keeping this V sat as active and V reference as 0. So, from V saturation I am getting R2 into V saturation divided by the total R1 plus R2, and if for the next time if V reference is active and V saturation is inactive, then the reference voltage will come here, reference voltage into R1 divided by R1 plus R2. Similarly, the lower threshold voltage is calculated as, here what will be the difference here is, for the lower threshold voltage the output is minus V saturation. So, if the output is minus V saturation, you will be getting VLT. So, only the negative sign is the difference in the equation of the threshold voltages. So, what is hysteresis voltage? VH. This is hysteresis voltage, it is the difference between the threshold voltages. So, here VUT minus VLT will give you 2 R2 V saturation divided by R1 plus R2. So, these two will be getting cancelled, and this is the hysteresis voltage. And what do you mean by backlash or hysteresis in the output? Say this is voltage Vi, and here it is VUT for example, and up to here VUT is higher. According to the circuit, if VUT is higher, then the output is positive V saturation. So, it travels here, and if Vi is higher, it gets negative V saturation. This is for the first case, and for case 2, now it is plus V saturation and this is minus V saturation, this is V out, right. So, here for the case 2, the output becomes minus V saturation, right, and the reference voltage, say for at somewhere here, the lower threshold voltage is the reference voltage now. Now, the input is lower, the input is compared with the lower threshold voltage. So, it has the input is compared whenever it exceeds the input voltage exceeds the lower threshold voltage, until that point the output is minus V saturation. So, it travels from here. When it exceeds, or it becomes, when the lower threshold voltage is higher, then the output will be plus V saturation. When you combine these two outputs, you will be getting like this. This is one transition when the input is compared with upper threshold voltage, and this is another transition, another path when the input is compared with the lower threshold voltage. So, this is said to be the hysteresis. This is said to be the hysteresis voltage. The voltage, upper threshold voltage minus the lower threshold voltage, is the hysteresis voltage, and this is said to be hysteresis present at the output, that is the sharp transitions at the output. It is otherwise known as backlash, and this is the one of the disadvantage of the regenerative circuit. And what is the main application of the regenerative comparator is, it converts a slowly varying sine wave or a slowly varying signal into a perfect square waveform. That is the main application of the regenerative comparator. And next circuit is square wave generator. It is otherwise called as astable multivibrator or free running oscillator. The principle of generation of the square wave is to force the op-amp to operate in saturation region. The fraction of output beta is fed back to the input terminal. Thus, the reference voltage V reference is beta V naught and may take the values plus or minus beta V saturation. And here the output, the states, two states of the astable multivibrator is quasi stable states. Both the states are quasi stable states. And one more important point, we are not at all giving any input to the circuit, external input to the circuit of the square wave generator or operational amplifier or a astable multivibrator or a free running oscillator. So, the single circuit is called as square wave generator or astable multivibrator or free running oscillator. See, there is no external input signal given to the circuit, and the output is fed back to the positive terminal of the op-amp through the resistors R2, R3, and also the output is fed back to the negative terminal to the resistor or R or F, and this is a passive integrator. After integration, the output is fed back to the negative terminal of the operational amplifier, and these are the compensated techniques used here. And this is the output waveform as well as the capacitor waveform of the square wave generator. And see, this is also the application of a comparator, because it is the output of the circuit is transited between again the positive and negative V saturation values, right. So, when the output is positive V saturation, the capacitor starts charging, and when it reaches beta value, beta V saturation, it gets discharged. The output is also become negative V saturation. When we see it in the circuit, if the output is, consider for the case if the output is positive V saturation, the value, voltage value given to the positive terminal is plus beta V saturation, and beta is calculated from these two resistors as R3 divided by R1 plus R2 is beta. So, beta V saturation, and the same voltage is charged by the capacitor through the resistor RF. And while charging, if the capacitor voltage is just exceeds this voltage beta V saturation, then the output becomes minus V saturation, because this voltage is just exceeds this voltage, then the negative terminal will have a higher voltage. So, the output will get transition from plus V saturation to minus V saturation. When this is minus V saturation, what is the value at the positive terminal? It is minus beta V saturation. If it is minus beta V saturation, what happens to the circuit now? What happens to the capacitor now? The capacitor is now discharging towards the output value through the resistor RF. The output value is minus V saturation. And now, while discharging, the capacitor voltage, if it becomes slightly lesser than the voltage at the positive terminal, that is minus beta V saturation, then the output gets transition from minus V saturation to plus V saturation. That is what given in the waveform. So, consider the output is plus V saturation. This is plus V saturation, and what happens to the capacitor now? The capacitor starts charging towards plus V saturation. So, this is the voltage beta V out. Here V out is nothing but saturation value. Beta V saturation is given to the positive terminal, that is the reference voltage. So, when the capacitor voltage is slightly greater than, just it crosses beta V saturation, the output gets transition from plus V saturation to minus V saturation, and also the capacitor starts discharging towards the output. And while discharging, when it is slightly less than minus V out, and this is the voltage given to the positive terminal when the output voltage is minus V saturation. And so, if it is slightly lesser than this minus V saturation, and the output will get transition from minus to positive V saturation, again the same cycle repeats. Now, we have to calculate what is the frequency of oscillation. Since it is a free running oscillator, we have to calculate the frequency of oscillation. For that, the capacitor voltage is normally given as the final voltage plus initial minus final into e power t by RC. The capacitor voltage is given as Vc of t is equal to the final voltage plus the initial voltage minus final voltage e power minus t by RC. So, here we have considered that the final voltage as V saturation, and if it is a final voltage, what is the initial voltage of the capacitor? It is minus beta V saturation. Here you have to substitute in Vc of t. So, you will be getting V saturation plus initial value is minus beta V saturation minus V saturation e power minus t by RC. And here if minus V saturation is taken out, you will be having 1 plus beta e power minus t by RC. And what about this Vc of t? At t is equal to T1, Vc of t is beta V saturation. At t is equal to T1, that is here, this is T1, this is T1, this is output, and consider this as capacitor voltage, and here at this T1, this is the capacitor voltage, say it is beta V saturation. So, substitute this value, you will be getting beta V saturation is equal to V saturation minus V saturation into 1 plus beta e power minus T1 by RC. So, now if you take out this V saturation and move it to the left hand side and take natural logarithm, this exponential term will be go out. So, finally, this T1 is given as RC into natural logarithm of 1 plus beta by 1 minus beta. This is the value you will be getting for this T1, and T1 is only for the half cycle, and for full cycle you have to take 2 T1. So, you will be having 2 RC. This is for total time period of one full wave, and this is for the design purpose also they will be asking design a square wave generator for the time period 1 millisecond. So, you have to take it for the whole cycle, it is 1 millisecond. In that way you have to design the square wave generator. So, the summary is we have seen the comparator, types of comparator, that is inverting and non-inverting comparator, application of comparator as a zero crossing detector. Also the comparator can be used as a time marker generator, phase generator, and zero crossing generator. The square wave generator also we have seen, and Schmitt trigger, otherwise known as regenerative comparator. These are the important topics we have seen today. Reference questions to check the knowledge. What is a comparator? Discuss comparator as a zero crossing detector. What is regenerative comparator? What are the other names of square wave generator? Thank you.